तो नहीं करना ना, यहाँ पे रिकॉर्डिंग चालू है।
पूरी वो लाइन।
वो लाइव स्ट्रीमिंग चालू है। ओके। Okay. So, good morning, Iming.
Hey, good afternoon.
So we'll start.
Yeah, let's start.
Yeah. So welcome all for the session. Yeah. So over to you.
Okay. Yeah. So yeah, welcome to the afternoon session. So we'll continue the discussion on guided waves, SHM, and in the afternoon session we will learn the imaging for the guided wave SHM for particularly for the probability diagnostic imaging. And also we will learn the damage detection using the baseline free time reversal. Then in the lab session today, we have two options. One option is we will have a case study on the time reversal imaging for signals in the soil applications that we will discuss one aspect of time reversal that we can use for soil and root imaging. The other option is we can go over one of the ongoing project we are now conducting for U.S. Department of Transportation using structure light. Right. If we have time, we can go over both. But if we don't, we will have the option one covered. Okay, so that's the plan. Okay, so SHM and our online monitoring using ND sensors. Well, we discussed about the differences between ND and SHM. Well, as I said, there's a lot of overlapped domains for ND and SHM. And particularly if we can combine what we learned in non-destructive evaluation for novel sensor development with the monitoring techniques for SHM, that we can make the structures and materials not only smart, but also we will bring a lot of interesting problems when we're dealing with data processing and inverse problems. So this is a schematic of a funding project about, I believe, about 10 or 11 years ago at MSU, where we developed a online monitoring of structure framework for using guided waves. Okay, so multiple sensor nodes are shown here on the structure, where each sensor node is implemented using a PDT sensor. Everything is being developed using wireless communication protocol and communicate with the base station for information fusion after data analysis, then having automated analysis for damage diagnosis, right? So we covered the basic concepts of data processing, information fusion, and automated analysis for other applications. Here, there's another example of doing that. For the sensor node, there's a computational core on the sensor node where you have the microcontroller facilitate with the PDC sensor for actuating the sensor and also performing the sensing where you collect the data. Well, when you have the data, you can have them stored and then transmitted to the base station. The other components are the power, and this is a wireless. It can be either battery powered or it can be, you can have some energy harvesting schemes there. In day 5, we will talk about advances in the 4.0, where we will touch some of the applications where we have completely battery-free sensors. I think that's some recent development in this area. Well, in this lecture, we'll talk about the guided wave SHM, where we have the PDC sensors there. Using the PDC sensors, we will not only excite but also receive the ultrasonic guided waves. So what is guided waves? So it is a elastic stress waves, as we've seen in today's morning session. Those waves guided by multiple reflections from surfaces of the structure. So the natural waveguides are plates, shells, rods, and beams, and it has a complex, dispersion curves, or the group velocity versus the actuating frequency. Here you can see at different actuating frequency, the group velocity will change over f. And you can also have different modes showing there from S0, S1, S2, S3 to A0, A1, A2, and so on for symmetric motion and asymmetric motion as shown here on the right. So the guide waves can, they are dispersive and they will propagate in multiple modes at even the same frequency. This morning, we seen that we can select some preferred wave mode for the simplicity of data processing. Right, so for example, here, if you chose 500 kilohertz, then you only have S0 and A0 mode. It is suitable for house monitoring of structures, and they can be efficiently used to inspect multi-layer structures, for example, lap joints. And we've seen lap joint structures in the previous application. The simulation of guided waves, in quasi-isotropic plates can be done using the FEM in Abacus. So let me show you, this is a video. Let's play this from the beginning. So excitation is a Henning windowed 5-cycle burst. So Henning window is something similar to cosine, but it's why it's not from here. Let me see. Okay, so it's actually Henning profile 5 cycles burst with center frequency at 100 kilohertz. So you can see the simulation of those waves propagating, and the displacement field is being shown here. So for composites, you can use SHM to you can use guided wave SHM to monitor the waves propagation and reflection in these layered structures. And another interesting structure is a PI joint or pi joints. where you'll see the shape of the structure is like a pie, and this is a very critical component in structure, which bear the loadings. And you'll see a new method developed for probabilistic diagnostic imaging for guided waves, where we utilize statistics and also inverse problems for NDE to get the data from images. So what is PDI? Simply speaking, if you place two PDT sensors at these two locations where the ellipse is constructed here, and the sensor are located as foci here, PDT1, PDT2, and with the mathematical knowledge we know about ellipse, that the any point, if the defect is any point on those dashed line, that the distance or the radius here, LA to D and LD to R, or we define as L actuation or actuator to defect, or and the distance between the defect to the receiver. If you add these two distances together, it's always going to be the same, right? So that's how what's the properties when you have this two distance added together when the defect is on this ellipse. Well, this tells me that for this setup, when I have a transmitter or receiver or actuator and receiver here, that I have the equally probability when I have the defects seen on this ellipse trajectory. Well, for this PDI, of course, we need multiple measurements from different sensors to get image formed. And we also need to statistically tell, okay, what is the most probable damage location with multiple sensor nodes there. And by knowing the property we just mentioned, the numerator here is going to be the same. If we are looking at the defect along the same ellipse trajectory, by assuming the groove velocity is the same, or we are looking at the same wave mode. So we can calculate the time of flight for the defect, where if they are on this ellipse, they're going to be the same. Okay, so this picture shows you the time of flight of defect when you have the actuation. Then baseline means there's no defect, and when you have defect, you can calculate the differences. So you call this a difference signal due to the defect. From that, you can calculate the TOF for defect. This shows you the setup, and you've already seen some similar concepts in our pattern technology, where we can have an array to pick up the signals from the actuator. This is a simple demonstration. And we use the laser vibrometer to sense the outer plane displacement in a non-contact way. All right, so you have the laser vibrometer pick up to give you the measurement from a stand-up distance there. You can also have the actuator and the receiver pair here to pick up the readings from the guided wave propagating from the actual location to the receiver location. By looking at a particular wave mode, here we choose the A0 mode. And the difference of A0 mode group velocity at various propagation angles is less than 10% at frequencies less than 200 kilohertz. And this is demonstrated in this plot here. A0 group velocity versus angle. And the PDI can be applied to locate damage in the woven composite material, which is shown here with the geometry, 450 times 630 times 5 millimeter cubic. Well, after we categorize the guided waves in all directions, now we just embed the sensor into this composite plate. In this configuration, we have multiple PDC sensors here, which can be served as both receiver and transmitter, and introduce a impact damage with several millimeter diameter. It's actually shown here. Then you look at the data from each individual pair, and using the PDI, as I said, you are drawing or you are statistically determining the possible defect location on the ellipse. Then by adding the ellipse from each pair, because you know the distance between those each pair, for example, this two pair, and this two pair, you can actually get your ellipse, derived from that, and you can get the most possible defect trajectory on the ellipse trajectory by knowing the group velocity in all directions. And you can use the time of flight information to infer the possible locations by adding up all the possible locations of the defects. So you can get a PDI ellipsis. The data processing tells you that by adding all those possible locations together, you will have some convergence in spatial domain. That for the entire plate here, you only have 6 PDT sensors, and by adding that up together, you will have the most possible location of defect, showing here with the highest probability, found here. With thresholding, you can get the most probable location using the geometric mean, which give you a very accurate estimation where the damage is. In this case, you pick the actuation frequency, so you can select the A0 mode to identify the damage for the time of flight calculation. And you will need to do geometric mean when you are doing this statistically averaging here. Then to reduce or to improve the accuracy and reduce the false indication of damage, where you'll see it in other locations here. Okay, so this is a very fast inversion for the guided wave methods. Instead of using data reconstruction, like what we did in tomography, right? For multiple transducer and receivers, we can also do tomographic reconstruction. So this is a well-established method that you can do reconstruction where you have multiple transmitter receivers. It's not necessary to be in a ring geometry. In this case, you can also apply that. The only difference here is the location of the transmitter receiver pairs. But by using these nice properties of the ellipse and statistical data processing, you can get the most possible location, here identified as a defect location. This can also be applied for complex geometries, and the complex geometry here is the pine joint, or this is actually a widely used joint as a stiffener for the structure. It is very difficult to inspect the joint location because the geometry here and other similar geometry you've seen, similar to the pine joint, is, for example, the rail track. If you look at the cross section of that, it's like I shape, right? And you'll have those rail head, a rail web, and rail base. And if you have defect there, because of the geometry, it's quite difficult to inspect. And in this case, if you have two materials, you have the stiffener, which is metal, you bond it with the composite to make this a pine joint. If there's defect at the joint location due to the bonding, or there's any defect in the material, you can use this sensor network to determine where the defect is. Similar configuration, you can have multiple PZ sensors there. We've done this with embedded sensor in the material, here the composites. And use the PDI, you can get the most probable location after data processing. You can identify where the defect is. Right? So this is another example of it. The next example that we want to discuss using guided wave SHM is to perform time reversal technique for dissimilar material lab joints monitoring. And this is a baseline free time reversal technique, which we'll see very soon why I call it baseline free. If we apply fatigue loading, or if the structure is subject to fatigue loading, then you will have defect originated and growth over time. One key structure is the lap joint structure. You've seen this a lot in aviation industry. You've seen this a lot in automotive industry in the previous lectures, right? So the lap joint structure, as I discussed this morning, that in aviation industry now you still see that widely in the in-service aircrafts, where they use rivets, mostly titanium and aluminum rivets, to join those structures together. So if you go to inspect the aircraft, or before you just enter the aircraft cabin, you can look at the aircraft fuselage, the skin. There you'll see a lot of rivet holes there. That's how they joined those different structures, different layer structures together, and to form the lap joint configuration here. In this case, we continue our same structure this morning. So I picked this in our lecture. So we have a better understanding where you can have a bond line to join two materials together. And the material here can be metal and composite. So we call it dissimilar material bonded joints. Well, this is actually a joint that will bring challenges in the maintenance because they are dissimilar in material properties. So when you are subject to the same loading, the loading can be mechanical loadings, it can be the thermal loadings, for example, the change of the temperature. Due to the differences in material properties, the cracks are more easily to be developed at a dissimilar material joining location. But the advantage of this dissimilar material joining is it definitely can reduce the weight. So you can replace some of the metal with lightweight but composites. With the bonding here, it makes easy in fact manufacturing. So it's extensively used in aerospace, marine, and automotive industries and more. So the defect there, how we can monitor and characterize that efficiently and effectively, that's very important. So you can demonstrate this using a tensile test where you apply tensile forces on this lap joint. And you can clearly see with the damage, the force displacement or the strain stress curve here shows you the damaged joints will fail much earlier than the healthy ones. Well, you can use guided wave as a monitoring technique for understanding the energy transmission between those lap joint structure. So a little bit more complicated than what we discussed this morning when we demonstrate the reversible adhesive composite structure or reversible adhesive bonded conversible structure, RBCS. Now we are dealing with dissimilar materials. The substrates can be different in materials. So we make it a little bit more complicated. And because of that, we'll have a lot of mode conversions at the interface to make the signals more complicated. So we will deal with more sophisticated signal processing algorithms here. And the PDT itself can actuate multiple modes simultaneously, as we can see from the previous dispersion curves. Those different wave modes plus mode conversions occurred as discontinuities. In this case, which is shown here, they can be sensed using the same sensor or same type of sensor, and then we can do data processing. The advantage is very obvious that you can make very low cost and small size sensors. It can be PDT, PVDF, and so on. You can actually cut those sensors into small patches and attach it to the structure. The maximum sensitivity to distance inspection and imaging is achieved by selecting the optimal guided wave inspection parameters. So this is a flow chart telling you, how you can do guided wave inspection tailored for this particular distance detection. So the geometry and the material properties will be well understood, help you to determine the dispersion curves, and you can use that to select the different modes and frequency you're working on. This leads to the PDT design and the optimal placement of the PDT on the structure. Guided by the simulation, and this will further help us to study the signal response from numerical simulation, for example, FEM modeling, and through experimental validation, you can give a feedback loop where we will determine the modes as well as a frequency for the operation of this technique. So optimal mode shape needs to have both in-plane and out-of-plane displacements inside the adhesive layer. So that guides us to select the modes, and the wavelength should be small enough to detect the given size response, because the resolution is determined by the wavelength or the actuating frequency here. And the PCT should be designed and tuned to selectively accurate the mode of interest. So this will also give us the guidance for the PCT design. Okay, so for the similar material lab drawn here, this is the experimental setup, and the side view of this in-house made this similar material drawing. It shows you the aluminum layer and also the composite here, the glass fiber composite layer with the dimension shown here, and you can also see the glued in between. The bond line width is 160 millimeter. The top view and bottom view is shown here with aluminum on the top and GFRP on the bottom. You have the knowledge of those material properties, and you can see the difference between aluminum composites in terms of density, Young's modulus, and Poisson ratio. And also you'll see the material properties for the adhesives, and also the PET sensors on on the surface of the material. And as I said, first of all, you have to do a study to understand the dispersions, and this is very critical for you to decide what frequency to choose. This shows the phase and group velocities versus frequency for this particular structure, where you have the composite joined with aluminum and the epoxy layer in between. So you can see only fundamental modes are actuated at frequency less than 120 kilohertz, right? So you draw a line here that you will only looking at the fundamental frequency A0 and S0 there. The phase velocity of quasi S0 and A0 modes do not converge to shear wave speed, so the structure is not symmetric with respect to the midplane, right? So you'll select your actuation frequency below 120 kilohertz. So you only look at the fundamental wave modes. So this slide showing you the study of actuation frequency, mode structure, and wavelengths. So the mode shape determines the amplitude of XYZ components of the particle displacement, and it can be evaluated for selected wave modes at different actuating frequency, as you can see from the previous slide. And now for A0 mode and S0 mode, you can get the displacement at different thickness. As you shown here, we have a thickness, in our study, it is 4 plus 4.5 with a few millimeter epoxy in between. So you find that the quasi A0 mode at 105 kilohertz is suitable for the spawn detection due to the high in-plane as well as outplane displacement in an adhesive layer. And you can also, from this figure, you can tell, you know, what happened at S0 mode. So you will also select mode actuation using frequency tuning. That you select, the different frequencies, so you can understand the wave mode and also the propagation of guided waves when you deal with this complex boundary geometry. And when you have this boundary area, when with or without that, what will happen? So you can study the PZT on aluminum, PZT on composite, PZT on this joint geometry, and what happened if you have this boundary area there, or a delamination area. So a lot of work needs to be done before you actually apply this to a complex geometry. So you study the PET strain transfer in aluminum only and composite only. You can get the fundamental wave modes, normalized strain versus frequency to understand the strain transfer. All right, with all those fundamental understanding, and also simulate the structures you are looking at here, then we will move this to the sensor configuration, sensor design, sensor configuration, and deployment or placement here. We work on this technique using the pitch and catch approach, similar to what we did in the classical pitch and catch ultrasonic testing. Now you just use one as a transmitter and the other as a receiver, and then get the signals when it propagate from one TX to one RX. So you have two strategies for one is within the bound sensor placement. There, the sensors are placed in critical areas where the spawn may occur, and you have lower attenuation of signal due to smaller distance between the sensors, and vice versa. And the boundary region should be wide enough to allow more than one row of PDT sensors. Across a bound sensor placement, the large distance between the sensors help to avoid overlaps on multiple modes in collected signals, and the signals will contain converted guided wave modes due to discontinuities. So you'll have, as the picture showing here, the A is the within bound sensor placed here. You also have the across bound sensor placement, so which is showing as configuration B here. This is just a tailored sensor configuration for a structure we're having here for the GFRB composite bonded with metal, aluminum here. And depends on your structure that you should develop your own sensor placement strategy. If you have no knowledge at all, then the previous sensor skin configuration might be a good candidate for doing that, where you have fixed distance between sensors that bring you the simplicity of doing sensor data processing, but also give you more flexibility of moving the sensor array on the structure. So you can see the philosophy behind that when you have knowledge of what you're looking at, or if you have limited knowledge, then how you can choose your sensing and data processing strategy. This is the actual sensor placement for the fabricated lab joint with dissimilar materials. Now we can try to understand the baseline free monitoring for lab joints using time reversal. So what is time reversal? We will see time reversal in ultrasonics here. Of course, for the lab session today, we'll try to look at the time reversal techniques for microwave. So in other words, the time reversal is not limited to one form of physical waves. And it can work for both mechanical and electromagnetic waves. If you have a wave equation in its PDE form. So wave equation means that you have the partial differential equation as both second derivative with respect to time and with respect to space. Okay, so with the wave equation, you can solve for the wave equation. Let's assume that we are solving that in a simplified, let's say, Helmholtz equation. And you solve those solutions for the solutions of those wave equation in the time domain. And where you have the wave propagating from the transmitter to the receiver, you have the sources of the wave emanating from the transmitter locations and received at the RX or receiver locations. If you do the time reverse, or you flip the time, make it negative t from t, then you can now treat your receivers as the new sources of waves. And you do the time marching in negative time to backpropagate the signals or energy from the receiver locations. And you will converge at the transmit locations. This is a simple explanation of time reversal technique. Why this is important? Well, it looks trivial when you're actually dealing with this time reversal when you have the known transmitter and receiver locations. But think about this. If you are having signals reflected or signals originated from the discontinuities, here discontinuities can be defects. Then if you only know the signals received at the receiver's location, now you make those receivers as the source of those waves or energy by using the time reversal technique. Then you can backpropagate those received energy or waves back to where the defect is. So this is how this time reversal can be used to get the defect location identified. Now, in this case, you'll use this guided wave propagation to demonstrate the idea of damage monitoring and identification for lap joint geometry. Hope that is clear. So we said the fundamentals and hopefully the concepts is clear here. The advantage of this technique is it compensates for the dispersion of composite materials when doing the time reversal and requires comparison of the received signal with the actuation waveforms, and the usage of baseline is minimized. That you don't really need to have the baseline information when you have the time reversal in this form. So let's see why is that. When I have the setup shown here, the simple setup, you have a PDT sensor A, you have a sensor B. Well, the actuation from PDT A can generate Lamb waves, the surface waves propagate in the material that you received by sensor B, and you'll have the received signal like this. You window and reverse the received signal, as I said, mathematically, you're applying the time reversal by flip the sign of time t there. So you'll flip it. A simple illustration here is just flip the waveform by along the t equals 0 axis, right? So you flip it to get the time reverse signal. You play back or back propagating the signal from B to A. Now B is like the new source of energy. and becomes a new actuating location. So you can have a receive signal at PCA. You compare the receive waveform at PCA with original actuation, then you identify the damage where it will distort the reconstructed waveform. Why is that? If you have damage in between, right, it will distort the signal when you are received at B, then you use this distorted waveform back propagate, you may hit the damage again, then you have the damage information in this time reversal signal. And you don't really need the baseline information. By only comparing the differences, then you can get the damage information. So we start with finite element simulation. Here, this is a 2D time reversal simulation in a bond line problem. Everything done is in Abacus. You simulate the wave propagation in the bound line. Here the setup for choosing the A0 mode here. You actuate at PDC1 and using the point displacement at the edge of the PDT to simulate the excitation of the waveform. And you can have this 5-cycle burst with a heading window profile. And this shows you the actual, side view of this bounded structure, where you have a PDT1 and PDT2 separated by 293 millimeter. Well, you select your actuating frequency, as we said, you have to select that frequency below 120 kilohertz. And you calculate the voltage at the receiving PDT by a summation of the in-plane strings at its bottom surface, and assume that the voltage is proportional to that. Okay, so this is how you simulate the PZT and get a measured voltage signal out of it. Because in Abacus you can only get your displacement or strings simulated, and you need to convert this into the actual measured voltage for a PZT sensor. So you have your forward, now let me play the video here. So you have your forward wave propagating from PZT1, right? This is actuation here. Then you'll receive the guided wave. You'll have different wave mode there, as you can see clearly from this simulation. And you can identify the symmetric and asymmetric fundamental wave modes. And you pick up the signals at the sensor location, okay? Then you will backward propagate those time reversed signal. You just do the time reversal there. This is a time reversal guided wave. Then you back propagate that back. Let's see. Now the PDC2 becomes a new source location. And it will back propagate into the PDC1. And the reversal of a multiple guided wave modes introduce artifacts in the reconstructed signal here, as you can see from this signal. This will, this is a reconstructed actuation waveform at PDT1, comparing to the actual, the original actuation waveform. You can clearly see a difference due to the multiple wave modes. They propagate at different speed, and also you have the edge signal showing here. Well, don't confuse this with a guided wave inspection, where you're dealing with the signals and also you have the edge information showing there. In that case, you need to process the signal, understand the time of flight features from different wave modes there, But here we are just demonstrating in a simple simulation that's showing you the effect of the edge and also different wave modes and the the resulting artifacts due to that in the time reversal. Okay, now this is not the real signal we collected, like we are doing other guided wave monitoring problem. So we need signal processing to get the time reversal signal back. And this also shows the simulation where we can understand the guided wave scatter from the emanation in bounded line. This is 3D simulation. We choose our actuation frequency to only look at the fundamental wave modes. And we see that the A0 mode shows strong reflection from this bond as predicted from the analytical solution, where, as I mentioned, we have two sensors here. We have a despond, and you can clearly see the despond or delamination response here from the A0 mode reflection from our simulation. And from this simulation, it also show or validate that for the A0, S0 group velocity agree well with analytical dispersion curves. This gives us the validation of the model, and then we can use this for this study follow on. Well, this is actual experimental testing and validation, where we have a C-scan of the damaged region, or the C-scan of this bond here. We have multiple sensors to form a sensor network. We also do, as I said, the C-scan of damaged region using the water immersive ultrasound. Right. So the data here is not coming from the PET sensor network, but you are getting more like ground truth information from the water immersion scan. And the C-scan of this bond obtained at a much higher frequency, 20 megahertz, using reflection from the bottom surface of aluminum layer and adhesive. Right. Then you can use this time reversal technique to identify the damage location. In the morning session, I'm sorry, and actually we discussed it in the beginning of the afternoon session. We introduced one method called a PDI that can also be applied here, right? This is the second signal inversion technique for us to do the data reconstruction. Well, as I said, there are different ways of doing tomographic data reconstruction. And similar to what we did in the beginning of this afternoon session, let's try to use the same diagnostic probabilistic imaging to get the location. And you can see it's very similar here. You can either use a elliptics, or you can use classical tomography reconstruction here. The problem here is we need to deal with the ill-posedness issue, that you may have not one or unique solution. So we can also see that damage can be sensed even if it lies slightly off axis between two PDT sensors due to the diverging wave field pattern. And by considering that, we can apply a Gaussian probability density function in 2D, then you can consider that probabilistically where damages are. So if you look at this under a classical tomography reconstruction approach here, you can show it here in the schematic. Or in this case, you can simply using time reversal. And for each pair, you can let the wave propagate back from the receiver side. Then you can make the energy converge at the possible damage location. So here, the time reversal will be applied, and you then use the symmetry of the structure or the configuration of the sensors to compare the reconstruct waveform as similar wave paths. And you can use a tomography reconstruction to evaluate where the damage is. So there are many inverse problems involved here. And I suggest you to read the reading materials that I posted by Professor Temprino, that 45-page tutorial. I haven't actually talked about that in my lecture, but I assigned that besides lab sessions, so you can read and get more understanding of different inverse techniques. Okay, so now let's look at some of the results here. So I have those PET sensors labeled. Now I have the pairs 3, 7 and 3, 9. Let's look at those two pairs. I can have a reconstructed actuation waveform obtained as I just explained. You propagate, for example, from 3 to 7, then back propagate from 7 to 3, and when you have 3 to 9, you have the defect along or near the path of 3 to 9 here. Then when you back propagate, you have the damaged information embedded in the time reversal signal after you compare with the original signal from 3. So this shows you the raw data where you have the pair 3.7 and pair 3.9 and the same actuation waveform. And you'll see the damage pass from 3 to the healthy pass from 3 to 7 and damage pass from 3 to 9. You can definitely see a difference. And then when you calculate time reversal, you can clearly see the damage information is actually being embedded here. Of course, you also see the multiple wave modes and the reflection of the edges for the lap joint structure here, even for the healthy path. So it's not exactly the same as what you've seen in the original actuation waveform. So the defect can be calculated using a damage index defined here, where you are doing the integration over a time here, time 1 to time 2. It depends on the structure and wave velocity, and the damage index is defined in a way that has been normalized, where you have the original signal and time reversal signal. You are actually calculate the differences between the original time reversal, and with the normalization, 1 minus this square root term. So you can define your damage index to be 0 if they are identical, and if it is 1, then that's completely dissimilar, right? So this is a normalized damage index. Of course, you can have different ways of looking at it. You don't really need to normalize it. You can look at the actual physical meaning of it to get the damaged images, but this is just one way to look at it. And you can also you need to assign weights to each detected wave path based on the configuration of the sensors, and the statistical reconstruction will tells you where the damage is with the highest probability here. So you can actually get this is the comparison between the reconstructed damage location versus the true damage location, and you can see it aligns very well. It tells you where the damage is. Of course, you'll see some errors here, well, due to the number of sensors, the way you configure sensors, and also associated uncertainties. One thing I will point out to you, although I don't have the results here for the uncertainty quantification analysis, but that needs to be done. And think about how you're going to do that to quantify the uncertainties so you can better understand the errors in this case. And another statement I want to make is any problem we're learning from this lecture. This lecture is called Introduction to NDE Inverse Problems and Data Processing. We're dealing with the fundamentals, the physics of imaging for NDE problem, how to form images from the signals and signal processing. You have to think about quantifying the uncertainties in the imaging process or the inverse problem process, so that you can have a meaningful data representation and the interpretation, right? So keep that in mind. So I think with the past 2 days lectures, I want to make that very clear to you that why UQ is important. The conclusion of this module that we can successfully apply PDI for impact damage detection for GFRP plates and response detection in the PI joints. We actually see that in the first part of this lecture. We identified optimal actuation frequency, wave shape, and sensor placement for baseline-free response detection, because in a time reversal, you don't really need a baseline. You just need to consider the differences by comparing the received signal after the time reversal technique. We develop FEM simulation and we demonstrate it is important for us to understand the sensor configuration and design. And everything's being demonstrated experimentally to locate the damage. Although we haven't done the Elson quantification, but it's something that you can think about for each application here. So this is the end of this module, and I think I want to make this discussion for day 3 coherent, where we start from the discussion of ND and SHM. We adopt one application out of all the possible ND methods there. We choose guided wave to understand the basics of basic concept of guided wave and how we can use guided wave for some interesting applications here, the dissimilar material drawing, the complex geometry, where we will lead to different mode conversion, and guided wave signal processing, and imaging for the structural health monitoring problem. And we also demonstrate how we can use a model assist approach to perform the inversion or the imaging of guided wave signals for this particular problem, right? So with that, I will take a short break, and I will try to go to our case study session or lab session. We'll further understand the time reversal technique from a different application, which I call signals in the soil. If time permits, we'll go to another case study where we have optical structure light technique for data reconstruction. So let's see, if that's possible. Anyway, with that, I would like to take a 2-3 minutes break to answer questions. Or you want to have a break, we can use this couple minutes to do that when I'm opening up the other course material.
And let me check. Any questions from the audience?
Okay, let me open that.
I don't think there's any questions. So
Okay, that's fine. Let's take a couple of minutes break here when I'm setting up.
yeah, we'll take a
session. Yeah.
So we have one question: how many maximum receivers can be used in time reversal techniques?
Okay. Thanks for the question, Shankar. This is let me first answer your question. There's no limit of maximum number of receivers in the time reversal technique. I don't think there's a limit there. Of course, the more the better. This is a quick answer that the more the sensors you have, of course you're gonna get more information, and when you do the time reversal, you'll get a better results. But that's not possible, right? Instead of asking the maximum receivers to be used for time reversal technique for a particular problem, I'd rather to ask this question is what's a minimum number of receivers can use for time reversal to get the same or adequate detection or categorization results, right? Because that's more useful. That you don't really need to put many sensors out there. If you only put the sensors at the strategic locations with minimum number of sensor, which means minimum burden for data processing, then that's better, right? If you can place a lot of there, of course, that's ideal, but you don't want to do it. Yeah, definitely. If you want to have all the receivers, if you want to use all the received signals for time reversal, definitely that means more computational time. Okay, let me
Yeah,
share
I
my
think
screen.
any questions? Okay, or should we proceed with the next course material? Yeah.
Let's proceed to the next course material. Well, I realize this section that I put in day 4 Then since day 4, tomorrow, we will only have the morning session given by me, and the afternoon session there will be a lab session that I would like to spend more time completing the lab assignment I gave you. So we'll move the tomorrow's afternoon lectures to today. That's why we have a couple of options here. So, but I like to cover this first option since it's directly related to time reversal reconstruction, but for different application. Okay, so
So
let's.
the tomorrow's lab session will be on COMSOL, or it will continue with MATLAB?
We'll continue with MATLAB. I hope the student
Okay.
can finish the MATLAB assignment and submit it. The deadline is actually today, your local time. But I'm okay that if you can spend tomorrow's lab session and working on that in the afternoon. Okay, so this is a application that we combine novel EM, ND sensing, imaging, and time reversal with plant phenotyping. And plant phenotyping is a key area for precision agriculture or smart agro-food system research. So the word of phenotyping is a simple way of looking at is you want to look at, for example, the morphology, for example, the shape, the size of a plant. And in this particular research problem, what we've done is we want to get a plant phenotyping through the root imaging. This will be really challenging because we're dealing with the measurement when we have the signals in the soil. And soil in itself is a very challenging material that will attenuate signals. Think about ultrasonic signals in the soil. It will not propagate very long distance because the airs, the different composition of the soil, it will attenuate the mechanical waves significantly. That's why you don't see a lot of ground penetrating technique using ultrasonics, right? Well, for EM, it's possible. So that's why you see GPR using radar technologies in the soil, so you can have some, low resolution signals. Of course, you can have different way of doing the GPR measurement or geophysics measurement there. And that's beyond the scope of this class. But if you're interested, as I point out at the beginning of this lecture, the geophysics problem when we have the buried object, and you can have different ways of exciting and receiving the energy when we deal with those soil or geophysics problem. So first of all, let me set up the stage by understanding root imaging. As I said, it is important for gram phenotyping. And what is biomass analysis and how we can use our NDE inversion or inverse problems to understand the biomass analysis. Well, everybody knows roots of a plant. We have all experience of looking at the roots. You understand that it is a complex geometry, and the root system itself not only is complex and three-dimensional, it's also very it resides in a very complex environment, and it provides functions central to the plant fitness, such as water nutrient acquisition, and the plant health and survival are dependent on the root system architecture. So for the plants, how that work in our entire ecosystem is capture the CO2, carbon dioxide, and transfer the carbon from the air to the soil through the roots. The modification of root structure architecture could contribute to improvements of desirable agronomic traits, such as yield, drought tolerance, and resistance to nutrient deficiencies. So we need to understand the root structure or root structure architecture. Well, there are different ways of doing it. In agriculture fields, there's dedicated research field understanding the root structures. Well, how we can have or take advantage of new sciences and automated engineering tools to help the agricultural research to accelerate and hopefully revolutionize the process of measuring root. And also, as I said, the root itself is complex. Also, surrounding environment is also complex. So if we can understand the soil characteristics and overall the complex root systems, that is important. Well, the state of the art of root imaging evolves in two directions. There's a lot of work going on there for high resolution methods. For example, using X-ray, CT, using MRI, and also there's ongoing work, but I don't think it go anywhere. That's my personal opinion. This is a ARPA-E DOE project done by Stanford. I give a reference there so you can read it if you are interested in using thermal acoustic imaging. We also did that using for biomedical application. I show that to you in my introduction slides. The purpose of there is to get high resolution, high spatial resolution. The second is by compromising the resolution, I want to get high speed or high throughput methods. For example, optical technique, hyperspectral imaging. This give you very pleasant imaging speed. Well, somewhere in between, this is where we want to combine both high resolution and high throughput. Together, we call this ultra-wide banded microwave imaging. So by doing a better job of root imaging, you can help to get increased carbon stored in soil, improve soil structure, better fertilizer use efficiency, better crop yield, reduce topsoil erosion, and also for the phyto sequestration by better understanding the root systems. Of course, this is a very high level and ambitious role that we want to achieve by understanding the simple root structure through NDE method. Our preliminary results have been published last year, and you can actually search my name, root imaging, you'll find a paper published using ultra-wideband microwave imaging. And I list a couple of research here that you can read further if you want to get more information on what other people have done so far. So for microwave ND imaging, you've learned this in course number 1. We haven't actually talked about the physics of it. I know some of you are working on microwave imaging. So for root imaging here, where we have to deal with the root and also the soil at the same time, we know that soil is a very challenging medium in terms of an energy and material interaction. While at the same time, from our experiences for microwave NDE, it is becoming more important as an effective method to inspect lossless or low loss dielectric materials. and evaluate hidden or embedded objects in the structural medium. So by understanding the microwave energy and its interaction with soil, this is important for us to do an good root imaging using microwave. We also know the scatter field depends on the dielectric properties of the medium, so it provides unique electromagnetic and give you hopefully more information about these materials. So advantages of microwave NDEs are not just limited for soil or root imaging here. They are usually non-contact methods. It enables high resolution in the near field. It can work with single site access, and it can perform at large stand-up distance using the far field microwave imaging system. Some of the recent successful applications for microwave NDEs are corrosion detection, flaw detection for example, in the sprayed-on foam insulation of the space shuttle, this flaw detection of CFRP strengthened cement-based structure, and so on. And we also did microwave imaging for apples. So I just want to show this interesting project we published on ASABE, where we can, using microwave antenna to illuminate fruits here in an apple and measure the reflection or the transmission coefficients here, then tell if there's any bruises or internal damage in the fruit by looking at the microwave signals. This is an interesting project I just want to point out. So some conclusion we can draw from here that we can have simulation experiments done. Previous results show that the simulation show that the microwave TR imaging, transmit receive imaging, can be utilized for in single and multiple roots inside the soil. This is some previous work we've done, but there's some technical gaps here that we need to determine the feasibility of the system with respect to other factors such as moisture content, soil hardness properties, and depth penetration. And we also want to make this into a 3D imaging, as we show that root system is a complex 3D structure. For experimental, we have some success so far, but also we want to have a better hardware system. And I will go to some of the details to show you why that. So for novel hybrid EM imaging or sensing, the overarching goal is if we can develop and deploy, then validate an integrated platform which will connect a series of innovative sensors that we can get the key information for roots, soil, and plant, and get the properties of that, so we can enhance the soil carbon sequestration and all other biogeochemical goals. And the sensor should be designed to be non-contact, high resolution, high sensitivity, high throughput, yet inexpensive, and massively field deployable in the soil. This is very ambitious goals, but we realize that by cleverly tailor some of the EM sensor we have, we might make this possible. Broader communities of engineering, plant science, microbial, and for the people working in the agriculture, we can try to achieve a multi-modal, multi-physics, a large diverse data set to be collected and help to understand the complex plant soil interaction. So this is not just going to be a single effort from one area, but it should be a team effort. from each area to understand from a large and complex data set. The principle of time reversal, I just discussed that in the previous module, that if you look at the wave equation, in general, the phi term here can be either the electromagnetic, or it can be ultrasonics, depends on what physical quantities you're looking at. So it can be a general term. Then you can look at here, if you look in the EM application, now you can apply the time reversal operator to E and H, the electric field and magnetic field, by simply add a negative sign for the time here. So what you'll get is, if you have a microwave antenna for transmitting and multiple microwave antenna for receiving, you have something in between. For example, the blue dot here is a defect or root or something you want to image. You can treat this new antenna array for receiving as a new transmitting antennas using the time reversal technique. So you send a Gaussian modulated pulse here at center frequency 2 gigahertz. You get receive data, you time reverse it, right? You just flip it over time. Then you propagate this back. And we demonstrate this in simulation first. So this is a model-based back propagation results that you can focus at the defect location. Because when you have a transmitter, it will interact with the defect, then picked up by the receivers. Now, if you back propagate everything back, you'll have this energy image, tells you when and where this energy will be concentrated or peaked at the defect location by evaluating the integrated energy image. And there are different ways of calculating, the possible location of the focused energy area, right? So you can read our paper for more information, right? So this shows you the first model-based approach, where you can do the forward simulation for wave propagating in the material, interacting with the defect, and also the time reversal data inversion, where you can reconstruct the damage location. So this shows the numerical model for time reversal based on the FDTD simulator. This is actually a 2D, very simple FDTD formulation here, where you update H and E step by step in this time marching formulation. The time domain pulses and the frequency, or the Fourier transform that is shown here. If you choose a very narrow width time domain signal, that you can get an ultra wideband frequency around 15 gigahertz waveband to look at the details you want to image. We start with a full wave EMFS simulation, where we study no soil, soil only, and soil with a single root. And here root we use a caret, so we can adopt the material properties of caret. So from the simulation, you can see the signals in the time domain for the pulse magnitude versus different time, right? And for different scenarios here, you can see they have this different signals in the time domain. One thing I want to point out is it's quite challenging to look at the signals here in the time domain because they all looked like very narrow pulses here, and it's difficult to extract the signal features to tell the differences. Well, what you can do here is you want to do the reconstruction, right? And that makes more sense instead of looking at the signals in the time domain only. So you get the scattered signal from the receivers. In this case, you can put this in this geometry in simulation model that you have one source, you have multiple receivers. And after you get the receiver signals, you will backpropagate that and try to reconstruct that in the spatial domain. This tells you the two geometry where you have single root and the multiple root, and using time reversal, you can reconstruct the location of the roots fairly well with some noticeable artifacts there due to the numerical as also due to the scattering of waves in this simulation. Well, it's more important to demonstrate this experimentally, right? Simulation, you can always do that, but I always suggest you do simulation first, which will help you to understand a lot of things before you move to the actual experiment design. So you don't start from scratch when you design your system experimentally. So we develop a system here in our lab. So you can see the different Vivaldi patch antennas here. You have a circular track here that you can see we can perform the tomography reconstruction, where we can fix one antenna location and rotate the other one, so you can get a tomography setup. So you have one transmitter and the receiver in almost 3/4 of a ring, so you can get all the information measured there. The saw is in between, where we put this in a microwave transparent container. Okay, and the parameters actually being set up here. So what the goal here is, we want to demonstrate that we can make the microwave penetrate through the soil by measuring the receiver signals, perform data reconstruction. We can actually image what's inside the soil. We try different antenna design. So there are larger Vivaldi antenna, different from what we've seen before. And also we put different plants in it. I think the students are trying to be creative here to put green onion, carrots in it, celery with different dielectric constants. So we can get different signals and try to image those in the soil. Well, this is what we get in terms of the scanning parameter in the frequency domain in our 2019 measurement. This is our first set of measurement a little bit more than 3 years ago, before the pandemic. And we get some encouraging result at that time that you can differentiate the different configurations for soil only, soil with 1 carat, and soil with 2 carat in the transmission measurement where you look at S1, 2 parameters and its phase, and the phase information give you more interesting differentiating here. While for carrots with different sizes, you can also see some the difference there from large, medium, small, and SR frequency, you have monotonic relationship, right? So this is some interesting result we get. Of course, you can convert this in the time domain. I'm sorry, in the free time, time domain, because everything we measured using the VNA in the frequency domain. So we get a frequency domain measurement. That's a little bit easier to do. Of course, you can also have time domain microwave measurement down, but there will be a different instrument. So we measure everything in the frequency domain, then we convert them into time domain by using inverse Fourier transform. So you can see the signal is hard to differentiate from the time domain, but if you apply this in the time reversal, this is what we get. We call this the first set of measured data. You can see for large, small, 2 carats. And the white circle here shows you the true location of the carats. The results is not that great. You can see some indication of the roots, but a lot of artifacts out there. And well, we know that we have to assume the dielectric constant of the soil before we actually categorize that. I know some of you are doing that material categorization. So we realize for the time reversal data reconstruction, if you don't have a knowledge of the soil dielectric constant, then your results going to be significantly different. So we start with dielectric constant with 4, then we also realize if we assume that to be 10, you'll have much better reconstruction results comparing to 4, right? Top and bottom. Well, this tells us this uncertainty of soil property, which will affect the imaging results significantly. So we need to reduce that uncertainty by knowing better the soil properties. So another takeaway is here that by doing the first measurement, we had high position error. We have additional artifacts out there. And the correct choice of background dielectric properties are very important. Then we did the second measurement after a few months, right? So we changed the way we set up the hardware. We actually get better data in this case. And at different receiver locations, we get the 3 different receiver locations. We get the frequency domain data stored for different frequency information for different configuration of the roots. Here again, still carats. With the signal processing with this array imaging, you can see the array data at different angles. And you can clearly see the angle dependency. While still from a time domain signal, it's very difficult to see the difference. And we can use the time reversal to reconstruct data. In this case, we get a better understanding of the soil. We figure out that's probably around 6 for that particular soil. So we reconstruct image and also do the data processing. Here, the simple thresholding. You can clearly see the improvement over the first set of measurement a few months ago in 2019, that you'll have the reconstruct data clearly show you the location of the roots. And the roots actually happen at the highest intensity location. So you can do thresholding to further enhance the results. to achieve less position error. The position error definitely better than what we've seen before, right? So this is way off, right? And even you choose the right soil parameter, still there's some error, large error there. But in this case, you have a much better position accuracy, but still there's some artifacts showing there. Well, the third measurement was done after we improved the hardware and also the data processing technique. So this is a third data set done by the students. And I just want to show you the results for a third measurement. This is a video showing you the reconstruction. This is automatic playing, so it will playing in loops. So you can see the left one is the single root imaging in terms of the field intensity magnitude. So you can see the root will be reconstructed very well. Everything here is experimental, not simulation. So you'll see the real artifacts and noise in our data. But with this time reversal technique, and you can actually image the root location with fairly good contrast. Right, so you can see it step by step it will be reconstructed and focused at one area. This shows the window temporal signal at different time location, and you can see those are synchronized to each other. You can see the time domain signal when we are actually focusing at this location. This is near real-time imaging using experimental time domain data, because for microwave data acquisition here, it's very fast. And for the inverse problem here, the reconstruction is also needs minimal computational effort. If you deal with the data carefully, and you only pick up the signal features you want to use for the time reversal, and you can get near real-time imaging. And this is pretty fascinating that you can actually see the root almost near real time. So this is a sort of set of measurement data and its reconstruction results for the single root and two roots here. As you can see, the signal to noise ratio has been significantly improved. And also the position accuracy is very good. And you have a very concentrated energy at the location of the roots. Right? So this is a example I would like to use as a case study for our NDE inverse problem lectures when we talk about time reversal technique. And this is also an interesting application that we're dealing with the complex and large attenuating materials when we're dealing with soil environment. Some things that we have to consider here is, first of all, as we seen that we need to have a good understanding of the dielectric constant of the soil. While the dielectric constant of the soil varies significantly from type of a soil, we're considering, for example, if it is a clay type of soil, this is sand type of soil, or we have to consider different water content in the soil. If you have high moisture level, a low moisture level, then the loss tension there will be very different. And I see there's a question there. I think that's associated with what I was just discussing there. So what is the loss factor value of carrot? I don't know the exact number for you, but we definitely need to have a contrast between the roots and also the soil. Then we can have a good imaging performance there, right? So I believe you can probably have that information for our paper. I don't remember the number there, but what I want to discuss here is there's so many uncertainties here, and so much to figure out before you actually get a nice imaging results. The data inversion technique is not the only decision factor there, but how you can incorporate everything into the data inversion, into our inverse problems, that's more important. Well, let me give you some comparison between before and after and show each step how we can improve it over time. So we have some preliminary results. We do a better job in the system calibration. So we achieve second data set. Then we improve the sensor. So this is the result we published using the ultra wideband sensor, and we can actually have a better reconstruction results here. Of course, we also take care of the uncertainty analysis part, but we only take care of some of them because this is a very complex problem. Although we try to simplify that into a single root, multiple root, a cylindrical object assumption, and so on. Well, but comparing to what people are doing in the plant and soil departments or in the agriculture, this is a new technique that has not been done in the field, but has a potential, as I said, to achieve both high resolution and also high throughput because of the advantage of microwave sensing or imaging itself. People usually do a lot of work. They gather the core of the soil by extract the root with soil. Then they move that into the lab and do CT, computer tomography. Then you get the root imaged, get a 3D structure of it. But that's not realistic, right? That's not realistic when we actually want to deploy this in the field. The more realistic is we can have this fast EM imaging technique to get root imaging, root structure imaged. In your lab session number 1, in the material I shared with you, there is one figure for root imaging as well. That's where you can consider to use electric impedance tomography for root imaging. I have one figure there. If you have time, you can read additional materials using electric impedance tomography. That's a different physics where you work at a much, much lower frequency. The sensor will be different. You'll see those needle type of sensor in the soil. It's still going to do 3D reconstruction, dealing with similar challenges we identify here in terms of the soil uncertainties, well, the complexity of the root structures, and the complexity of a sensing system itself. But that's something that you can read further if you're interested in that. So let's revisit the conclusion. The same conclusion I showed you before. We didn't have. I think I skipped the summary results in simulation, but for experiment, that we have a few things to be done. For example, we can further develop a hardware system to obtain high contrast in data. We should reduce uncertainties associated with the soil. For example, the soil dielectric property should be extracted more accurately. Well, when we do this in the field, how we can do that quickly in the field and calibrate our system by passing the right soil properties into our reconstruction. That's challenging, but seems need to be done. And we can replace our frequency domain system with a pulse domain system in a time domain to obtain better pulses. This is another improvement in the hardware that we can consider. There's some ongoing work on signal processing using machine learning. This is ongoing work. I don't have too much results to show, and this is done by one of the graduate students that I work with in Colorado, that they can use machine learning to look at the data to try to use the input like empty no soil data and try to use the machine learning to suppress the noise and also make a better prediction to deal with the experiment data, right? So this is just some preliminary results. I don't have much to talk about here, but I just want to show you that you can consider to use machine learning in this case as well. This is still ongoing research, and I'm open for discussion and collaboration for this soil imaging, and there are tons of questions out there to be addressed. And if you look at the NDE problem we've seen so far, and if you want to apply NDE, particular here imaging, inverse problem, reconstruction to a new domain here, the agriculture, you'll see, well, there's a completely new area with so many different challenges out there. And for NDE, what we've looking at so far, we already deal with complex materials. But if you're dealing with the agriculture, that's a new magnitude of complexity with different uncertainty considerations there. But, well, the hope is there, right? The methodology we develop in one can be adapted into another one, or adapted to another one, if you understand the fundamental physics of imaging and also associate data processing challenges, and that definitely can be done. And from this lab session or case study, that we clearly demonstrate that we can apply what we learned here in the NE to a new domain if you carefully take care of some of the key technical challenges here, with a lot of challenges to identified. Okay, so that's what I want to share with you for the afternoon lab session. And as I said, tomorrow we will look into another aspects of signal processing, where we'll look at the feature extraction, principal component analysis, and machine learning. And that's supposed to be day 3, but I switch that with day 4 material. So we will go back to follow the syllabus. We'll talk about that on day 3. We only have morning session tomorrow, and lab session in the afternoon. I hope you can spend more time to deliver your MATLAB project for EIT. And you have more problem to work on, as I identify here. I already give you some hint in my lab materials for root imaging. That's also possible if you want to. If you finish that, if you want to, work on that a little bit further, feel welcome to do that. And I'll be happy to give you guidelines offline if time not permits within a 5-day course. Okay, so that's where I'm gonna stop here. I believe it's a few minutes before 4:30, and we'll have time for Q&A and discussion. All right, so I stop here. Any questions?
One question is there: how to choose microwave probe?
Yes. I assume this question is for root imaging only, right? Because this is a very big question. For root imaging, how to choose microwave probe. You've already seen that for this particular application, that we want to have a ultra wideband microwave so we can have more information extracted from the measurement. So one thing that we want to have is we want to design a microwave sensor which will have a broad frequency range. So this is one thing that we figure out. So a narrow band will not work very well in this case, unless you know exactly what you're trying to image. In this case, you have a very complex composition of the material with different type of soil and roots. So we realize that a short pulse in time domain, wideband in frequency domain is what we should focus on. The second selection of microwave, we try different design of microwave sensor, different size of microwave sensor, and for making this root imaging feasible in the field, that you have to consider how I can put this on underground in the soil, right? So the size consideration, also the material consideration, the design aspect of it, how that can sustain the field condition, that should also be considered here. All these questions should start from simulation studies. With that, you'll have a rough understanding of what type of microwave sensor I should design. Then you can think about in the actual measurement and how you should fabricate and deploy your sensor there. So this is my answer to your question. If I understand, this is for root imaging only. Well, for other applications, the answer might be completely different.
Thanks.
How to select frequency. As I said, this is ultra wideband, right? So you actually, what we did, we actually sweep broad frequency bands. If you know, as I said, if you know, what problems working on, what frequency is good, then you'll probably have the frequency selection question to answer. But in this case, you're going to have a broad frequency covered. But in general, the frequency optimization, you can do that through simulation. And of course, from experimental, that you can definitely do the optimization problem there. But for this problem, we cover a wide frequency band. Okay, microwave sensor. Let me open this. It just
in microwave
sensor detect nanometer or micrometer range dimension defects in material. The answer yes. Actually, the paper is already out there a few decades ago, but that's limited to the very small field of view. You can have a nanometer resolution microwave sensor. Those cantilever or tip-based sensor in the near field. If you Google near field microwave, you'll see those set up there. The resolution definitely nanometer. You can see that, but that's not very practical for a lot of industrial applications because you can only see or image a very small field of view. The sample has to be prepared, and that has to be very small. What frequency range requires? Well, you can refer to that paper. As I said, the frequency is not a determining factor there for the high resolution, because the resolution at nanometer or micrometer is not determined by the radiation frequency anymore. It's determined by the resonant setup in the near field. So the frequency is still like we're seeing in the microwave range, right? That's why it's called near field microwave. but the sensor is very, very small, so you can get high resolution images. Okay, very good. Okay, any other questions? I think we had very good discussion here.
Any questions from the audience online? Don't see any questions.
Okay, if no more questions, I'm always available.
There's one more. There's
Okay.
one more question that SAR technique for
Sorry.
microwave imaging is good.
I say that's good. If if the question like this, of course, synthetic aperture radar. Definitely, yeah. I think any technique has its own, good and bad. SAR has been demonstrated in quite a few applications. You definitely, you'll see it is good for microwave imaging, but it will not apply for all problems. And as you can see, we didn't actually use SAR here. So my answer is, yeah, it's application and problem dependent, and you'll see a lot of very good results from SAR.
Okay. Any other question?
Okay. With that, I'm very glad that we have our Thursday lecture completed. I hope that everybody's are still with me and enjoying the lectures. So with that, I will see you guys tomorrow in the morning. Good luck with your assignments, and see you tomorrow.
Okay.
Yeah.
Thank
Okay.
you.
Very good. See you. Bye-bye.